Okay, so in talking about the intermediate value theorem, or commonly referred to as just the IVT, and you can state IVT when you're doing your, right, by your reasons, by the IVT. You don't have to say by the intermediate value theorem. You can use the three letters, the abbreviation. Okay, so there's three things that we have to show on the intermediate value theorem. We have to first show that our function is continuous on a closed interval. Okay, some of the other value theorems are open intervals, but this one is closed on a closed interval, so between two x values. Okay, number two, the y values aren't the same at the endpoints. Okay, that's what that means. The y values are not the same. And then k, this value k that we're going to be looking for, is between your two endpoints. Okay, because it wouldn't make much sense to talk about something that's not between the endpoints. Okay, so if those three things are true, then there's some other value c. So this is an x value. Right, that's an x value. Between your endpoints, right, these are your endpoints of your function, for which there is a y value. Okay, so in other words, the y value is in between there. Yes, that's some very mathy things, but let's talk about what that means in pictures, because usually pictures are much easier to understand than words. So in other words, if we have some function, and here is the lower bound x, and here is the lower bound y. Okay, so this is some x value a, and this is some x value b. Okay, so we have some random y value, right? And then we have another random y value, right? So now the f of b, the y value here, is not the same as the y value there. Yes, agreed? Okay, there's some, right? So these are the points, f of a and f of b. Okay, so if our graph is continuous, right, it has no removable discontinuities, it has no asymptotic discontinuities, right, it has none of that stuff. It's continuous. If it's continuous, then there's some letter in here, c, right? There's some other x value we're calling c, such that there is an associative y value in between this interval, right? That's what it's trying to say. That if this is continuous, right, if our graph is continuous, then there's going to be a y value in between your max and your min, right? Your lower bound and your upper bound. That's what is guaranteed by the intermediate value theorem. Okay? Could there be other values? Could there be a some random thing up here? Right? Could there be another up here? I mean, there could be, right? Maybe our graph was quadratic or something and went up like this, right? That could happen, but it's not guaranteed. Okay, the only thing that the IVT guarantees is that you're going to find a y value in between these two y values. Okay, that is what the intermediate value theorem guarantees. That if you once were 3 years old and now you're 10 years old, that somewhere in between there, you were 6 years old. That's all that the IVT says. Okay? So let's look at some, let's look at some problems so we can actually see what there is to do. So here are a couple of examples. Number one, determine if we can even use the IVT. Okay, so first of all, we're checking for continuity. Is your function continuous on the closed interval? Right, on the closed interval from a to b. So that's first. Okay, and then we're going to find the endpoints. We're going to find f of a, the function evaluated at your endpoints. And we're going to make sure that they're not equal to each other. Okay? And then we have to make sure that our value k is between those two endpoints. Okay, because if it's not between there, then there's no guarantee that the intermediate value theorem is going to work. Okay, so these are the three things that we have to check in order to be able to use the intermediate value theorem. Okay, so here is our function 1 over x minus 2. So if we remember what that looks like, that is a rational equation that has a vertical asymptote through positive 2. And we're looking for the interval from 2 1/2 to positive 7. Okay, so 2 1/2 is going to be from here to positive 7, which is, bless you, way over here somewhere. Okay, so this is our closed interval from 2.5 to 7. Okay, so first of all, is our rational function continuous on the interval from 2.5 to 7? Right? Sure it is. Are there any holes? Are there any asymptotes? Are there any of those things at all? No, because our function is rational, right? Because f of x is a rational function with x not equal to positive 2, right? That's the only place that is discontinuous, is at positive 2. F of x is, in fact, continuous, U-O-U-S, on the interval from 2.5 to 7. Okay, so we're going to use our English writing skills, your ELA, and we're going to write exactly what the IVT states for continuity. Our function is rational, therefore it is continuous, right? The only place where it's not continuous is at positive 2, and positive 2 is not in our closed interval. So our function is going to be continuous. Check, right? Number one thing, continuity is checked off the list. We have a rational function, okay? Number two, let's find our endpoints. So f of 2.5, right? So we're going to find our endpoints, which is 1 over 2.5 minus 2. 1 over 0.5 is 2. 1 divided by 1/2 is 2. So when x is 2.5, our y value is 2. Okay, so that's on there. There's our left endpoint. F of 2.5 is 2. Now I'm quickly running out of space, aren't we? We'll save number 2 for later. So how about f of 7? F of 7 is 1 over 7 minus 2, which is 1 over 5. So 1/5 or 0.20, yes? 1/5 is in there. So somewhere way over here, we're going to have 7 comma 1/5. Right? So check. Our endpoints are not the same. The right endpoint is less than the left endpoint for our closed interval from 2.5 to 7. Okay, so now we have to check the third thing. Is 2 between, is 1/4 between 2, right? So this is our k value, is 1/4. Is that between 2 and 1/5? Is 2.0 less than 0.25? Is that less than 0.20? Is 2.5 less than 0.20? Is 25 cents less than 20 cents? No, right? This is not true. That is not true, which means that 1/4 will not necessarily be in this interval. Okay, so in fact, we cannot use the IVT in order to say that there will be a y value of 1/4 on this interval. Okay, so the k is your y value that we're trying to look for, right? Is there an x in here that gives us a y value of 1/4. Well, not guaranteed by the IVT because 1/4 is not less than 1/5, right? 0.25 is not less than 0.20. Well, rethink. Let me rephrase, right? It's got to go this way. 2 is larger. Is 0.25 larger than 0.2? Oh, my brain. Right, this way. 2 is the greatest. So here, right, usually f of a was, well, now f of a is greater. So this is the way that it's got to go. So sorry, my brain. That is in fact true. 25 cents is greater than 20 cents. Oh, amazing. So yes, by the IVT, there exists, so a lot of words, right? There exists a C, right? A C value on, what is our closed interval? 2 1/2 to 7, right? That's our closed interval that we're talking about. There exists a C value on this closed interval such that f of c equals what? F of c equals 1/4. Okay, so that is the conclusion of our intermediate value theorem. Yes, it was continuous. Our rational function is continuous. The left endpoint and the right point are not the same, and our k value is in fact between them. Okay, I just got to make sure I get my my greater than symbols correct. So our k value that we're looking for, which was 1/4, is in between our two endpoints. Okay, so if all those things are true, then there exists a c value. I'm not asking for you to find that x value, right? I don't want to find it. We're just saying that one exists. That's all we're doing by the intermediate value theorem. Okay, so there is an x value that we're calling c on this closed interval such that the y value of that c is going to be 1/4. Okay, so that's how we use this intermediate value theorem. That's what the majority of your assignment is going to want you to do. Can you use the IVT here? And if you can, maybe go ahead and find it. Okay, so number 2. Let's see if we can get our brain working correctly the whole entire time on this problem. So we have a function that is a polynomial. Let me write it over here, because I'm going to scooch over. X squared plus 5x minus 6. And our closed interval is from -1 to 2, and we're seeing if there's a y value of 4 in there somewhere. Okay. X squared plus 5x minus 6. What type of a function is this? This is a quadratic, aka a polynomial. So because f of x is a polynomial, all polynomials are continuous. And you can say quadratic, right? It's definitely a quadratic, but it's also a polynomial. Because f of x is a polynomial, f of x is continuous on all of the, like on R, right? On all of the real values, but definitely on the closed interval from -1 to 2. Okay, so if you're dealing with a polynomial, anything with a linear or a quadratic or a cubic or a 4th degree, all of those functions are continuous everywhere. So of course it's continuous on the closed interval from -1 to 2. Okay, yes, you have to write that down. You must explicitly say that it's continuous. Okay, don't assume that everybody knows what you know. Yes, you're the smartest person in the room. That means everybody else is less smart than you. So tell them, yes, it's continuous because it's a polynomial. Okay, part B, we have to find our endpoints. So f of -1 and f of positive 2. Okay, so negative 1 squared is positive 1. 5 times negative 1 is minus 5. And then minus 6 means I have an endpoint of negative 10. Okay, and then 2 squared is 4, plus 5 times 2, which is 10, minus 6 means I have a y value of 8. Okay, and now for our third stipulation. Is our k value between negative 10 and positive 8? Okay, and our k value was 4. So is 4 between negative 10 and positive 8?
Yes.
The answer is yes. Yes, it is. So because all of these three things are true, it is continuous. We have unequal endpoints, and our k value is between there. We can say yes by the IVT, right? There exists a c value on this interval between negative 1 and 2 such that, there's a symbol for such that, I think it's this. I think that's the such that. But let's don't use that in case it looks sloppy. Such that f of c equals 4. Right? That is what the IVT says. Just that there is one. There exists a c value where there's a corresponding y value of 4. Okay, so that's how we're going to use the IVT here in calculus, is just to say that one exists. The three stipulations, the three things are matched up, right? They work. They are validated. Therefore, there has to be a y value in there of 4. Okay, so you have some questions on your assignment that deal with those kind of things. Okay, so there we go.